Welcome back, everyone. Lesson 4 brings us further applications of differentiation. In today's video, we will cover optimization, related rates, particle motion, and linear approximations. When we seek to optimize a function, we are to find the best possible outcome, which occur when the function reaches a maximum or minimum value. For example, we might try to maximize for profit, size, or strength, or minimize for cost or material usage. Question 31 asks us to maximize a store's revenue. The store's revenue can be found by multiplying the unit price by the number of units sold. This is a price times quantity calculation. We are told that, for every $5 off the price, the store can sell 10 more units, and this simplifies to a 1:2 ratio. This information will be used to develop a revenue function that builds on the given price and quantity. The given price is $450, and the given quantity is 200 units. However, as the store decreases the price by X dollars, it increases the number of units sold by 2x. The revenue function that we have just created forms a parabola in the xy plane, and its maximum can be found without calculus. Simply locate the zeros of the two factors, and realize that the maximum value of the revenue function would occur at the precise x value in between these two zeros. That x value is 175, and this number can be used to find the price and quantity that yields the greatest revenue. To maximize revenue, the store should set the unit price at $275 so that it can sell 550 units in return. The maximum revenue can be found by multiplying the new price and quantity. How would we use calculus to solve this problem? We could locate this maximum using our knowledge of derivatives, because we know that the derivative, or slope, at this maximum value is 0. And one way to take the derivative of our revenue function is through product rule. Once we have followed product rule to take this derivative, we can set the derivative to 0 and solve the resulting equation for x. The x value where the derivative equals 0 is 175, just like we found earlier. Again, we would use this x value to find the new price, quantity, and revenue. Question 32 asks us to maximize the area of a rectangular field that gets enclosed by fencing along 3 sides. Since there is only 3,600 feet of fencing, there is a constraint on the amount of fencing that can be used. We will need to take into account this constraint when we maximize the area. A diagram can help you get organized and into a better position to write equations involving the fencing constraint, as well as the area function that we need to maximize. From our diagram, we can see that 2x plus y should equal 3,600, and that the area equals x times y. We should make a substitution to find an area function that is completely in terms of one variable. Once we have an area function in terms of one variable, we can locate the function's maximum. Just like the last problem, we have a quadratic function on our hands, and we can locate the maximum by first finding the zeros of the function, then identifying the middle of those two zeros. The x value that locates the function's maximum is 900. However, this process did not use any bit of calculus. If we were to use calculus to solve this problem, we would locate the maximum by setting the function's derivative to 0. Doing so will also show us that the maximum area occurs when x is 900. As a result, the dimensions of the rectangular enclosure is 900 by 1800. Please attempt question 33 on your own. Pause the video, then circle back when you are ready. Did you find that the dimensions of the box are 6√2 by 6√2 by 3√2, and that the volume of the box is 216√2? If so, you have correctly solved question 33. Question 34 asks us to minimize a distance between a point and the line y equals 4x. To solve this problem, we need to recall the distance formula. It is also helpful to realize that, in order to minimize the distance, we would need to minimize the quantity inside the square root, which can be viewed as its own function, and one that serves as a proxy for the distance itself. In other words, we just need to locate the minimum of this inside function, which we will be able to do once we have written the function in terms of a single variable. By bringing in the coordinates of the known point and making a substitution for the y variable, we will have a function that we can derive. Find the derivative then set it equal to 0 and solve for x. This x value represents the x-coordinate of the point on the line that is closest to the coordinate pair 420. Make sure to also find y, so that you write your final answer as a completed xy pair. The closest point on the line is the point 84/17, 336/17. Related rates. Related rate problems involve quantities that change with respect to time. As a result, the variables that we use to complete related rate problems are functions of time, and this changes how we find and represent their derivatives. Let's take the time now to differentiate the following functions with respect to time. The derivative of x is now x prime, or dx dt. Every time we differentiate a variable, we must tack on its chain, like x prime, which represents its rate of change. This is an offshoot of the implicit differentiation technique. Every time we differentiate a function of time, we must remember to multiply by its rate of change, whether we represent that rate of change as x prime or y prime, or dx dt or dy dt. Remember to abide by the rules of differentiation and recognize when to use product or quotient rules. In this last example, we see two different functions being multiplied to each other, so its derivative requires the use of product rule. Question 35 asks us to find the rate of change for the distance between the origin and a point moving on the curve y equals x squared minus 5. By drawing out the curve and locating the key points, we see that the distance between the 2 points forms the hypotenuse of a right triangle. We can use this right triangle to relate the distance to the point that is moving along the path of the curve. We should start by outlining the side lengths of the triangle, as well as their rates of change. The value of x is 3 and its rate of change is 0.5. The value of y can be found by using x equals 3 into its equation, and its rate of change can be found with its derivative, which requires knowing both x and x prime. Now that we have the legs of the right triangle outlined, we can move on to the hypotenuse, which represents the distance between the stated points. The length of the hypotenuse is 5, coming from the Pythagorean theorem. You might also recognize that our triangle creates the known 3, 4, 5 Pythagorean triple. But to find the rate of change of the hypotenuse, which we'll call d prime, we will need to differentiate the Pythagorean theorem because it does the best job at relating our given quantities. When we do, we end up with a relationship that includes our rates of change, allowing us to solve for d prime. Bringing in the values of x, x prime, y, y prime, and d, we should find that d prime is equal to 2.7 inches per second. We have correctly answered our first problem involving related rates. Our next problem asks us to find the rates of change for a circle's area and circumference. How should we begin? A good starting place is to write out the formulas for circle area and circumference. These equations will be differentiated, knowing that the quantities within them are changing with respect to time. The differentiated equations introduce the rate of change for the area and the rate of change for the circumference. We will just need to plug in the values of r and r prime, where it is appropriate. Make sure to include the correct units of measure in your final answer. The area, which is a measure of 2 dimensions, changes in terms of square feet per hour, but the circumference, which is a measure of 1 dimension, changes in terms of feet per hour. Question 37 is a related rates problem that can be answered by working with similar triangles. The problem involves a boy walking away from a lamppost. As the boy walks further away from the lamppost, his shadow changes in length. One of the similar triangles includes the lamppost, and the second includes the boy. It will be helpful to completely separate these triangles before filling in any known or unknown information. Let's write in the known and unknown quantities into each of the 2 triangles. We know the height of the lamppost, as well as the height of the boy. Then we can use the variable s to represent the length of the boy's shadow, and the variable w to represent how far the boy has walked away from the lamppost. Taken together, we should see that the length of the bottommost side of the larger triangle is the sum of s and w. We can also represent the rates of change of these variables as s prime and w prime. So what is the rate at which the length of the shadow is changing? Here, we need to find a way to solve for s prime, and this starts with writing a proportion for the corresponding sides between the two triangles. We can then modify this equation to make it easier to differentiate. By differentiating the equation, we get into a position where we can solve for s prime. We will just need to bring in the value of w prime, which is the boy's walking pace of 3 feet per second. We should find that the value of s prime is 1 foot per second. Now, what about the rate at which the tip of the boy's shadow moves away from the base of the light? This amounts to the rate of change of the bottom side to the larger triangle. That rate of change is w prime plus s prime. Since w prime is 3 and s prime is 1, we can say that the answer to part B is 4 feet per second. Question 38 is a related rates problem that involves an inverted cone. When we dash in the height and radius of the conical tank and compare it to the height and radius at the water level, we see the formation of similar triangles, which gives us a way to relate the height, or depth, of the water to the radius inside the tank. With these similar triangles, we see that the radius should always be 2/5 of the height. And this relationship is important because it gives us a way to express volume in terms of just the height, or depth, of the water in the tank, which will make taking its derivative much easier. We will now substitute this expression for the radius, clean up the equation, then differentiate it with respect to time. The differentiated equation gives us a route to finding h prime, which represents the rate at which the depth of the water is changing. After isolating h prime to one side of the equation, we can plug in the values of h and v prime. The correct answer is that h prime is about 2.5 feet per minute. Particle motion. The AP Calc curriculum includes particle motion problems, which require students to relate position, velocity, and acceleration, all functions of time. Position is often written as s of t, velocity, v of t, and acceleration, a of t. You need to know that the velocity function is the derivative of the position function, and that the acceleration function is the derivative of the velocity function. In other words, we will use the first and second derivatives of the position function to find v of t and a of t. Question 39, Part A. To find the velocity and acceleration functions, we will need to take the first and second derivative of the position function. Part B. To find the velocity at t equals 1, all we need to do is plug 1 into the velocity function. Doing so shows that the velocity is 24 meters per minute. But is the particle moving toward or away from the origin at this time? To answer this question, we will need to know the location, or the position, of the particle at t equals 1. When we plug 1 into the position function, we find that the position is 4 meters, which lies to the right of the origin. And since the velocity at this time has a positive value, we know that the particle is moving to the right, which means the particle is moving away from the origin. Next, when is the particle at rest? The particle is at rest when its velocity is 0. We can set the velocity function equal to 0 to find the moments in time when the particle is not moving. Solving this equation for time shows us that the particle is at rest when t equals 3 and t equals 5. Then, to find out the interval during which the particle moves to the right, we can make a sign change diagram to map the regions where velocity is positive. The velocity is positive between 0 and 3, as well as 5 and 10. When you write your answer in interval notation, be sure to use parentheses and brackets where it is appropriate. To find the acceleration at t equals 3.5, we just need to plug this value of time into the acceleration function. Doing so gives us an acceleration of -3 meters per square minute. But is the particle speeding up or slowing down at this time? To answer this question, we will also need the sign of the particle's velocity. From our sign change diagram above, we know that the velocity at 3.5 is negative. And because the particle's acceleration and velocity share the same sign, we have enough information to say that the particle is speeding up. Let's talk about how we can figure out when a particle is speeding up or slowing down. The particle is speeding up when its velocity and acceleration share the same sign, either both positive or both negative. And the particle is slowing down when its velocity and acceleration have different signs, where one is positive in value and the other is negative. Question 40 provides a velocity time graph. At t equals 0, is the particle moving toward or away from the origin? We need to know the particle's position and velocity to answer this question. We are told that the particle's position is 3, and the graph shows us that the particle's velocity is -4. The important fact here is that the velocity is negative, which means that the particle is moving to the left. A simple sketch of this scenario can help prove to you that the particle is moving toward the origin at this point in time. Part B. Is the particle speeding up, or is it slowing down at t equals 1? If we mark this location in our graph, we can see that the velocity is negative in value. We can also see that the slope of the velocity function is positive, and this slope actually gives us the acceleration. The main takeaway is that the particle's velocity and acceleration have different signs, so the particle is slowing down. Another way to see this is that the particle's velocity is headed towards 0 as time moves on, and this means that the particle will soon slow down to a stop. Part C. The particle is at rest whenever its velocity is 0. The zeros of the velocity graph occur when t equals 2 and t equals 8. We can find the acceleration of the particle from the graph because acceleration amounts to the slope of the velocity function. As it is defined, acceleration is the rate at which velocity changes. So all we need to do, to answer this question, is to find the slope of the velocity function at the specified values of time. The slope at t equals 4 is 0, and the slope at t equals 7 is -1. Again, these slopes give us the acceleration at these moments in time. But how can we get distance and displacement from a velocity time graph? To answer this question, we will need to find the areas between the velocity function and the x-axis to get a sense of the particle's movements. These shaded areas represent the overall movements of the particle, and we can use geometry to find each area. After finding each area, we should recognize that the areas below the x-axis are leftward movements made by the particle, and areas above the x-axis are rightward movements. This distinction will play a role later on. The total distance can be thought of as the total movement of the particle, so it doesn't matter if the particle moves left or right because both motions contribute to the particle's total movement. We can add all of our areas together to find the total distance traveled by the particle. Net displacement is a little different. Here we do need to take into account the direction of the motion, treating leftward motions as negative and rightward motions as positive. The net displacement represents the overall change in the particle's position, and we can use this quantity to figure out the final location of the particle. We just need to add it to the particle's starting position. The particle starts at 3 meters, and it changes by another 3 meters to the right, so the final location of the particle is at 6 meters. A linear approximation is when we use a tangent line to estimate the value of a function. Would a tangent line approximation lead to an over or underestimate at point A? This linear approximation would lead to an overestimate because the line lies above the curve at all nearby points. But what about at point B? A tangent line at point B would lie below the curve, and the line itself would underestimate the values on the function. This is because the points on the line are lower than their corresponding points on the curve. Do you see how this can relate to the function's concavity? Tangents in a concave down region would overestimate the actual function values, and tangents in a concave up region would underestimate them instead. Question 41. We need to write the equation of the line tangent to f of x at x equals -2. This means that we need to know the point and slope at this particular value of x. To find the full x-y pair, we will need to use the function f. Just plug in -2 into the function rule. Then, to find the slope, use the function's derivative, f', and evaluate the derivative, again when x is -2. With the known point and slope, we can write the equation of the tangent line in point-slope form. With this equation, we can find the y value specifically when x is -2.5. This y value, that exists on the tangent line, approximates the actual function value at this location. When we plug in the specified x value and solve for y, we find that y is equal to 13.5. But is this an over or under estimate? Let's justify our answer by using the concavity of the function, which can be determined with the function's second derivative. The second derivative is positive, which means that the function is concave up and the tangent line lies below the curve, and this leads to an underestimate of the actual function value. Pause the video and try question 42 on your own. Circle back when you are ready to check your work. Did you develop the tangent line using an x value of 4? This would be the easiest point to use, and the approximated value comes out to 2.0125. If you got this result, you correctly used a tangent line to approximate the value of a function. Lastly, we will now discuss the derivatives of inverse functions. But first, how are inverse functions related to each other? You should remember that inverse functions are functions with flipped x and y values. Investigation 16 tells us that f and g are inverse functions. Let's use the given points on f and find the slope between them. The slope between these points is 3. If these points are on f, what would they be on g? Since f and g are inverse functions, all we need to do is flip the x and y coordinates of each point. Now, let's find the slope between these 2 points. The slope comes out to 1/3. Since the x and y values flipped positions, the slope also flipped. The 2 slopes that we found are reciprocals of each other, and this was the point of investigation 16. You need to know that inverse functions will have slopes that are reciprocals of each other when using corresponding points. Do you see how this relates to their derivatives? Since derivatives tell us about a function's slope, we should realize that the derivative values of inverse functions are reciprocals of each other, so long as we are referencing corresponding points. Let's use this relationship to answer question 43. We should first distinguish between the point that is located on g and the point that is located on f. From the notation g' of 0, we should realize that 0 is an x value for function g. If we are to use the corresponding point on f, we would flip the x-y pair around, which means that 0 is now the y value on f. Since function f is known, we can find the missing x value. The missing x value is -1, and this is important because we will need this x value to find the derivative of function f. Once we know the value of f' when x is -1, we will be able to relate it to g' by using its reciprocal. By the end of this process, we can say that g' of 0 is 1/3. Question 44 provides a table of values that can be used to find g' of 4. While this 4 represents an x value for function g, it is the y value on function f. This means we should find where function f has a value of 4 in the chart. Function f has a value of 4 when its x value is 1. More importantly, this is the row that we'll use to find f'. In this row, f' is 2, and its reciprocal gives us the value of g'. The final answer is that g' is 1/2. You have just completed further applications of differentiation. Keep up the great work, and I'll see you in the next lesson.